In this video, we are going to discuss about how to prepare an alkenes. Alkenes can be prepared from elimination reaction. There are two main types of elimination reactions to prepare an alkenes. First, the dehydration of alcohols. In this reaction, it involves losing of water from alcohols. The second reaction is the dehydrohalogenation of alkyl halide. In this reaction, it involves losing of hydrogen halide from alkyl halide. In the dehydration of alcohols, the reaction involves the elimination of water molecule, which is the hydrogen and the OH atom are removed from the adjacent carbon atoms. In this reaction, the hot concentrated sulfuric acid or the phosphoric acid can be used as the dehydrating agent. For example, if we have an alcohols, the alcohols react with concentrated sulfuric acid and be heated. The hydrogen atom as well as the OH atom from the adjacent carbon will be removed to form an alkenes. Here are two examples of the dehydration of alcohols reaction. The first example is the reaction between ethanol with hot concentrated sulfuric acid to form ethene. In this reaction, ethanol will remove water molecule, which is one of the carbon with OH atoms will remove the OH groups of atom, and the neighboring carbon will remove the hydrogen atom. The next example is the reaction between 2-propanol with hot concentrated sulfuric acid to form 1-propene. In this reaction, 2-propanol will remove water molecule, which is the carbon with OH group of atom, will remove the OH atoms, and the neighboring carbon will remove the hydrogen atom. In the dehydration of alcohols, the temperature and the concentration of acid required to dehydrate alcohols depends on the structure or the class of alcohols. The reactivity can be arranged due to the class of the alcohols, which is reactivity will increase from the primary alcohols to the secondary alcohol and the tertiary alcohols. In the dehydrohalogenation of haloalkanes, which is also known as alkyl halide, the reaction involves the elimination of hydrogen halide from alkyl halide. In this reaction, there must be reflux in alcoholic potassium hydroxide or sodium hydroxide. For example, let's say we have a bromoalkanes, which is react with potassium hydroxide in ethanol solution. The reaction will involve removal of the hydrogen bromide, which is the carbon with the bromine atom will remove the bromine atom, and the neighboring carbon will remove the hydrogen atom. Between the two carbon will form carbon-carbon double bond, which is give a product of an alkenes. Here are two examples of the dehydrohalogenation of haloalkanes. The first example shows that 2-chloropropane is refluxed with potassium hydroxide in ethanol to form propene. In this reaction, the hydrogen chloride molecule will be removed. The carbon with the chlorine atom will remove the chlorine atom, and the neighboring carbon will remove the hydrogen atom. The next example shows that the reaction between 2-chloro-2-methylpropane, which is refluxed with potassium hydroxide in ethanol to form 2-methylpropene. The carbon with the chlorine atom will remove the chlorine atom, and the neighboring carbon will remove the hydrogen atom. In this elimination reaction, how can we determine the major product of alkenes? For a certain alcohol or haloalkanes, which is undergo elimination, can produce more than one alkenes. But since the reaction produces a few number of alkenes, how can we determine which one is the major product? In this case, Sutzeff rules is used to determine the major product. But what is exactly the Sutzeff rules? Sutzeff rule states that In elimination reaction, the alkene with highly substituted double bond or the carbon-carbon double bond which attach with a greater number of alkyl group is the major product and it is more stable. Let's take a look for an example on how to determine the stability of alkenes. The first structure shows that the alkene with carbon-carbon double bond has no alkyl group. The second structure shows the alkene with carbon-carbon double bond with one alkyl group. The third alkene shows that the carbon-carbon double bond with two alkyl groups. And the fourth alkene shows that the carbon-carbon double bond with three alkyl groups. And finally, the fifth alkene shows that the carbon-carbon double bond have four alkyl groups. The more alkyl groups that present or attach at the carbon-carbon double bond in the alkenes give a higher stability of alkenes. Thus, all these structures are arranged by increasing order of stability due to the increasing number of alkyl groups that attach to the carbon-carbon double bond. Let's take a look for an example of the dehydration of 2-butanol. In this reaction, 2-butanol is heated with concentrated sulfuric acid to give two types of alkenes. In this elimination reaction, the carbon with OH atom will remove the OH while the neighboring carbon will remove the hydrogen. In this case, we have two possible hydrogen atoms to be removed. If we remove the hydrogen from the left side, it will give the product of 2-butene. But when we remove the hydrogen from the right side, it will give a product of 1-butene. Between the two alkenes that has been produced from the reaction, which one is the major product? By applying the Sat-Zeff rules, we have to count the number of alkyl group that has been attached to the carbon-carbon double bond in the alkenes. The first alkenes, the carbon-carbon double bond, has two alkyl groups. While the second alkene, the carbon-carbon double bond, has only one alkyl group. According to the Sat-Zeff rules, the carbon-carbon double bond, which is highly substituted or attached with a greater number of alkyl group, must be a major product, or it is more stable. Thus, in this case, 2-butene must be a major product. Let's take a look for another example of the dehydration of 1-methyl cyclobutanol. When 1-methyl cyclobutanol is heated with concentrated sulfuric acid, it will give two types of alkenes. In this elimination reaction, the carbon with OH atom will remove the OH while the neighboring carbon will remove the hydrogen. In this case, we have two possible hydrogen that can be removed. Thus, it will give two types of products of alkenes. Since we have two products that can be produced, how can we determine which one is the major product? By applying the Sat-Zeff rules, the alkenes which is more stable or the carbon-carbon double bond with highly substituted or more alkyl group must be the major product. The first structure shows that the carbon-carbon double bond of the alkenes has 1, 2, and 3 alkyl groups, while the second alkenes has only 1 and 2, only 2 alkyl groups. Therefore, the first structure has a greater number of alkyl groups. Thus, it is a major product. Let's take a look for another example of the dehydrohalogenation reaction of 2-chlorobutane. When 2-chlorobutane is refluxed with potassium hydroxide in ethanol, it will produce two types of alkenes. Between the alkenes that has been produced, which one is a major product? In the elimination reaction, the carbon with the chlorine atom will remove the chlorine atom, while the neighboring carbon will remove the hydrogen. In this case, we have two neighboring carbon that can remove the hydrogen. Thus, we have two possible products that can be produced. The first product is when we remove the left side of hydrogen atom, so it gives 2-butene. While when we remove the hydrogen at the right side, it gives 1-butene. Between the two alkenes that have been produced from the elimination reaction, which one is a major product? According to the Sutzeff rules, the carbon-carbon double bond with a greater number of alkyl group must be a major product. The first structure, which is 2-butene, the carbon-carbon double bond has 1 and 2, which is 2 alkyl group. For the second alkenes, which is 1-butene, the carbon-carbon double bond only has 1 alkyl group. That shows that the first structure, which is 2-butene, has a greater number of alkyl group. Thus, 2-butene must be a major product. Another example shows the dehydrohalogenation of 1-bromo-1-isopropyl cyclopentane. When 1-bromo-1-isopropyl cyclopentane is refluxed with potassium hydroxide in the presence of ethanol, it gives two types of alkenes. Between the two alkenes, which one is a major product? The first structure shows that the carbon-carbon double bond has 1, 2, 3, and 4. We have 4 alkyls. While the second product shows that the carbon-carbon double bond has 1, 2, and 3. Only 3 alkyl groups. Thus, the first structure of alkenes with 4 alkyl groups is the major product.